So let's look at the one that says, on the back, 5%? Yeah, the 5% by mass solution.
Yeah, and I was.
Let's look at that, let's do that together, okay? So why don't we look at that, we'll go through that one kind of together, all right? And, all right, I don't know where to put the answers. Oh, and I brought my phone instead of my calculator. Honest to God.
You want to get,
Yeah. I have the sheet, I just don't have the answers worked out, and I grabbed my phone instead of my calculator. I'm all discombobulated today. All right, so it says how many grams of glucose, and they give you the formula for glucose. So C6H12O6. So we want to know how many grams of glucose we need to make 2,500 grams of a 5% by mass solution. So I want to make 2,500 grams of the solution. That's what I'm trying to make, all right? And what I know about it is that it's 5% mass. All right? So first of all, what's the solute? That's the first thing you want to ask yourself when you do this problem. What? Not how much, but what is the solute? The glucose. So the glucose, the C6H12O6, that's my solute, okay? And what's my solvent in this case? Water, right? It doesn't say, we're gonna assume it's water. All right? And so my solution is both. My solution is the solute plus the solvent. So when you look at this number, this 5% by mass, so this is what I was trying to get you guys to think about right before you left the other day. If it's a 5%, that means 5 grams of solute for 100 grams of solution, all right? So you need to know the definitions of these different terms, all right? So percent by mass is part over whole. It's solute over solution. Both things are going to be in grams. This percent thing basically means it's however many, whatever the percentage is, it's that many grams of solute for 100 grams of solution. That's what the percent is telling me. It's per 100, all right? So I want to make 2,500 grams of this solution.
multiply it by 25.
Exactly. So I know I want to find the grams of solute. I know how much there is for 100 grams of solution, and I want to make 2,500 grams of solution. So this is very similar to the way we attacked the problems when we used the solubility curve, okay? Like we knew what the solubility was per 100 grams of water, and we multiplied by the mass of the water that we wanted. So I basically just want to go through and do that math. So 5 times 2,500 divided by 100 is going to be 125 grams of solute, because that's what I had. That's what it asked me, was how much of that would I have to use. So I would have to use 125 grams. I lost the sheet. All right, so I know that I need 125 grams of this, right? And I know that I want to make 2,500 grams of that, all right? So how much water do I need?
You subtract the two.
I subtract the two, exactly, okay? So my solution is my solute plus my solvent, okay? So if I know how much solution I have, and I know how much solute I'm going to have to use, then the difference between these two things is basically going to be the amount of solvent. So it's just going to be 2,500 minus 125, and it's 2375 grams of solvent. My solvent is water, okay? All right, now how do I get a molality? So we know a percent by mass, all right? It wants a molality. So you need to know what these different terms mean, all right? So molality is that little m. It's moles of solute over, somebody just said it, kilograms of solvent. All right, so once I kind of delineated what everything is, all right, now I just basically have to get stuff into the right units, right? Okay, so I've got to get, my solute is in grams right now, I'm going to have to change it to what?
Or no.
To moles, right? And my solvent is in grams. I'm going to have to change that to kilograms, okay? So that's basically what I would set about trying to do now. How am I going to change a mass to moles?
Molar mass.
Molar mass. So, does anybody besides me notice that none of these right? All right, so the carbon is 12 and there's 6 of them.
Sorry.
It's 1 and there's 12. And it's 16 and there's 6. So I got 72, 12,
96.
96, yeah. I think it's 180. So I look up the molar mass. Where am I going to find those? Periodic table. All right, so now I want to change this from grams to moles. So I'm going to say 125 grams. What am I going to do with this 180? Am I going to multiply by it or divide? I want my grams on the bottom. Oh, you already did it. See, you told me you couldn't do this.
That was good, Jessica's up.
So yeah. Oh, your calculator is in like fraction mode.
Yeah, I have to go back and forth
All right.
between this and stats. I always
Yes, oh, you have to
switch
go back
my
and
modes,
forth.
Yeah.
All right. So 0.69 moles, you guys said? I'm trusting
694.
you. Yeah, we have 3 sig figs actually. It's 0.694.
Even with the 180?
Yeah, because that, I looked these all up to the nearest 10. This is 180.0.
Oh, yeah.
So I got 3 sig figs. So 0.694 moles, all right. Now, here's my solvent, 2,375 grams. How do I change grams to kilograms? I got it. So where are the grams going? Top or the bottom? Where are the kilograms going? All right. So now where's the 1,000 go? With the grams or with the kilograms?
Kilograms. 1
Goes
kilogram
with
is
the
1,000
grams, yeah.
grams.
Listen to the girl who grew up with the metric system. Right. So it takes the kilo is the only big unit we have. So it's 1,000 grams per kilogram. It's the only one that's bigger than the basic unit is going to be that kilogram. So this is going to be 2.375 kilograms. So now I know both things I need. I know moles, and I know kilograms, and I just plug in, and I'm not going to, you guys can plug in yourselves, you know, because I don't know how to use this calculator. So when you're attacking these problems, there's the things you want to focus on are the definitions of those concentration terms, okay? So you need to know mass percent, you need to know molality, and you need to know molarity. I'm not going to give you those on the test. You need to know those 3 concentration terms. All right, those are definitions. They're not really equations, they're definitions. You need to know those, okay? All right, and there were a few dilution problems on here. How do you feel about the dilution problems? Are we understanding how to use that equation? All right, so what I'd like is for you to give me this sheet before you walk out today. All right, but I also want you to listen to me while I'm talking, so.
So you can make your productions.
All right. Okay, so let's, oh, there it is right there. Okay, so let's finish up the colligative properties stuff. So you guys kind of did this in the lab yesterday, and hopefully you saw that there was a change in the boiling point and a change in the freezing point when you put the materials into the water. So what you typically would see is that when you add the sugar, that typically your concentration should have, or your freezing point should have gone down a couple of degrees. And then when you added the sodium chloride, and what did you keep the same about those? It wasn't the same mass, right? Because you had a lot more sugar than you did sodium chloride, so it wasn't the same mass. So what did you keep the same about them? The volume of the water. What else? How did you calculate how much stuff to get? You just did this yesterday. So what did you do? You weighed those up based on what? What did you?
Calculation.
Yeah, well, that's what I'm trying to get you to tell me, is what did you calculate?
Oh, the mole.
Moles, right, so you had 0.1 moles of each of those, so the idea is that you started with the same number of moles, all right? So what colligative properties are, these are properties that change based on how much stuff is floating around in solution, based on concentration, okay? So you started with the same number of moles of each thing, all right? The sugar dropped the freezing point about 2 degrees, but the salt dropped it about 4, all right? So the reasoning behind that is that what happens essentially is when I put sugar in water, it doesn't break apart. So every particle I put in stays the same. But if I put sodium chloride in water, so sodium chloride is what kind of compound? Ionic or covalent?
Ionic.
Sodium chloride is a ionic compound, so when I put that in water, oh, that one writes good. It breaks apart into 2 pieces, okay? So you started with these 2 things. When I put this in water, it doesn't break apart, the sugar stays together. This is my sugar, and this is my salt. So this one stays together, all right? This one gives me, even if I start with the same number of particles, this will give me twice as many particles, so it has a bigger effect, okay? And so you should have seen that the sugar lowered the freezing point a couple degrees and the salt a couple more. Usually they'll vary by a couple of degrees on the freezing point. The boiling points, the effect on the boiling point isn't as big, and so it's a little harder to see, but I would still expect you'll be able to distinguish that the boiling point was higher for the sugar and then even higher for the sodium chloride solution, okay? All right, so we're gonna kind of look at these calculations a little bit today, and I'm hoping I'm gonna finish this up. Oh, I'm gonna pick the pen out early. All right, so the boiling point elevation, so this is a colligative property. It depends on concentration. And this word elevation, that means it goes up. So the boiling point goes up, all right? So what we calculate when we're doing this is what we refer to as the change in the boiling point. So we can use this equation. This is a plug-in equation. This is an equation I would give you. You don't need to memorize it, all right? And basically what it does is it lets me calculate that little triangle. We used that for delta T before. So that little triangle means the change in. So it calculates the change in the boiling point, and it says that I can calculate it if I know this constant. So this thing is called the Molal boiling point elevation constant. There's a mouthful, okay? So basically it's the boiling point constant, all right? And this little m is what? Molality, okay? So it's based on, these calculations are based on molality. So this thing is a constant, and I look it up for the solvent. So if I'm putting something in water, I look it up for water. So there's a little table here, and this table tells me that for water, it gives me the normal boiling point, because I'm going to calculate the change, okay? So it gives me the normal boiling point, and then it tells me what that constant is. And so for water, it's 0.51, and the units on it are degrees Celsius per molal. So it's 0.51, a half a degree. So every time the molality goes up, boiling point goes up about a half a degree for one change in the molality, all right? So if I know what my solvent is, and I know the concentration of whatever I put in there, all right, then I can calculate what the change in the boiling point is, all right? Not a very big change, and that's why I'm saying you're gonna have to draw that graph, look at those flat parts, that's what you're gonna be looking at, is that flat part of the graph, and see what the difference is between the flat parts on the graph, all right? The freezing point, the equation looks almost exactly the same, but now it's a depression, and that means it goes what, up or down?
Down.
Down, so the freezing point goes down. So there's no plus or minus in this. I have to remember that if it's the boiling point, it went up, and if it's the freezing point, it went down, okay? One goes up, one goes down. So my range like spreads out, all right? So the change in the freezing point, these things mean the same thing they did before. N is still molality. This is the freezing point constant. And again, I look it up for the solvent. And if you look up water, for water, it's 1.86 degrees Celsius per mol, all right? The other one was 0.51, all right? So this is about 4 times bigger. You get a lot bigger effect on the freezing point than you do on the boiling point. So every time my molality changes by 1 unit, my freezing point drops 2 degrees, all right? So that's why you made these up at the same concentration, all right? This molality that's in here, though, is the molality after it's broken apart. And that's the key thing, all right? So I have to take into account the fact that it's possible that some of the particles are going to break apart. I have to actually calculate the molality of the particles that are floating around in solution. Not what I started with, but what happens after I put them in water. Does it break apart or doesn't it? That's what I got to ask myself. And so you have to subtract, okay, if it's going down. So when we talk about electrolytes, so electrolytes is a word we use for materials that dissociate in solution to produce ions, all right? And so what happens is I get a bigger effect because the particles break apart, all right? So if one, I'm going to say, molecule breaks apart, then I'm going to have a larger effect because I have more particles in solution. So I need a way to kind of account for that. I have to be able to come up with a way that I can figure out, well, what's the difference? How is that effect going to be taken care of, okay? Can't turn the page. All right, so we looked at sodium chloride before, all right? So sodium chloride gets broken apart into sodium ions and chloride ions, and they're showing me all the little water molecules surrounding them as they get broken apart, all right? And so the idea here is 1 mole of sodium chloride, when I put it in water, it dissociates to form, oops, I thought there was more there. To form what? Ions, right. 2 ions. All right. So it breaks apart when I put it in water to form 2 ions. All right. So I have to kind of be careful about that. I have to take that into consideration when I'm calculating the molality of the solution. So we have this thing called a Van Hoff factor, which kind of takes care of this idea that the particles break apart when I put them into solution. And the Van Hoff factor is given the symbol of I. It's equal to the number of particles produced when the molecule breaks apart. how does it break apart? That's what I want to be able to figure out is what's that number? So we multiply, we kind of stick it in the equation here, all right? So instead of just having the change in the freezing point is equal to Kf times I, we stick this Van Hoff factor in there, all right? So this is, basically I have to figure this out based on looking at how the stuff is going to break apart. So what's the Van Hoff factor for sodium chloride? What would I be? 2, right? So I equals 2. What about sugar?
No, it wouldn't be like 1, whatever.
Yeah, it was a trick question. Doesn't break apart at all, right? It's a molecular compound. It doesn't break apart, so I is 1. All right? So we're gonna, when I give you this equation, I'm gonna stick this I in there, all right? That I basically is how many particles the stuff is gonna break apart into, all right? So if it's ionic, it's gonna break apart into its ions. If it's molecular, it's gonna stay together, and I is gonna be 1. So the part we did not do in the lab yesterday, remember I said we're gonna skip a part? We had calcium chloride as another salt to test. So part of the problem is the lab is too long. If we do all 3 of them, it's hard to get through it. The other issue is we've had trouble buying calcium chloride that was pure enough to use and wasn't treated for, they used calcium chloride as a drying agent, and so we had a hard time finding reagent grade that we could buy and use in this lab. But regardless of all that, how does this break apart?
3.
Yeah, so I get a calcium ion. What's the charge on calcium? Plus what?
2. Oh, yeah.
Yep.
That's it.
And I have 2 fluorines, so these come off separately, so 2 Cl minuses. So for this, I would be equal to 3. All right, so the more pieces it breaks apart into, all right, the bigger the bang I get, okay? So why do you suppose we don't, so you can buy calcium chloride, by the way, in bags to like sprinkle on your sidewalks and like that in the wintertime to lower the freezing point and keep your sidewalks free of ice and like that. Why do you suppose we don't sprinkle it on the roads? It gives me better, what do you suppose? Exactly, that's exactly it. We use salt because it's cheap, all right? There's giant salt mines over in central New York, in Syracuse. There's tons of salt over there, so we have a ready supply of salt. So that's why we use it, even though it rusts the heck out of our cars. And all right, so I want you to look at those. Not going to do any calculations. I just want you to think about what we were just talking about. So which of those would give me the lowest freezing point? All right, if I dissolved them in water. These are all aqueous solutions, okay? So if I dissolve them in water, the more stuff I get floating around in the water, the lower my freezing point is going to go. So which one of these, they're all the same starting concentration, right? 0.1, 0.1, 0.1, 0.1, which is what you looked at in lab yesterday, the same starting concentration. All right, but which one's going to break apart to the most particles?
D.
How do you think this breaks apart?
Lithium and
Okay, it hasn't been that long. What's NO3?
NO3 is a polyatomic ion.
It's a polyatomic ion, right. That stays together.
So would
So
it be B?
that's only 2,
Yeah.
so it's going to be B, right. This one breaks apart into 3, we just looked at that. These are both 2. All right, so I equals 2, I equals 3, and then I equals 2 for these others. All right, so the one with the most particles, that's the one that's going to give me the lowest freezing point then.
For the C8 plus 2 plus 2 CL, you got 3 because one was 2 and one was 1.
Right, because these CLs are, there's two of these, so it's like I could write it like Cl minus and Cl minus. They're not stuck together like this thing is.
Right.
This thing doesn't come apart, that thing's stuck together because it's a polyatomic ion, okay? All right. All right, oh, look at it, it's dancing, okay, all right. All right, so the last colligative property that we're going to talk about is osmosis. So some substances, in particular, so osmosis is important in a lot of different applications, but in particular for you guys, since a lot of you are in allied health fields, in your body, all right? So we have what we refer to as semi-permeable membranes. And what semi-permeable membranes do is they let some things cross over and not everything, all right? So some molecules are allowed to cross and some are not. And a lot of times we think of this as they let little things through and they block larger things, but that's not always the case. So sometimes they're selective. They basically, in your body, have been designed, your body has evolved to a state where it knows what it wants to let cross membranes, and so you have selective membranes. So sometimes it's not just the size, sometimes it's charged things that are not allowed to pass, okay? So they can be very selective about what they allow to cross over. Most semi-permeable membranes allow water to cross over and nothing else. So they allow water through, but they don't allow any dissolved salts through, they don't allow hemoglobin through, okay? Whatever, they don't allow anything through except the water molecules, all right? So the solute can't go through, just the solvent. So when this happens, basically, what wants to occur here is that I want to end up with the same concentration on both sides of a semi-permeable membrane. I'm going to kind of draw this a little bigger over here. I want you to think about this a little bit. Let me do that one that's right. All right, so let's say that I have my semi-permeable membrane, all right? And I have a bunch of water molecules over here. So I'm going to use these white circles to represent water. So I got 5 of them over here and 3 of them over here. And I have 1, 2, 3, 4 of these. 4 of those. So these little black things are going to be my solute. I don't know what they are. It doesn't really matter. They're my solute, okay? So what has to happen essentially is that if the water is going to be allowed to cross, all right, it's going to do that until it gets the same concentration on both sides, all right?
Equilibrium.
Exactly. It wants to reach the same equilibrium on both sides. The reason for that has to do with the pressure that builds up, all right? So it's a fluid pressure. We haven't talked a lot about pressure. I think it's easier if you just think of it based on concentration, all right? But what has to happen is the solute can't cross over to even things out. Only the solvent can, all right? So if this is a semi-permeable membrane that allows water to cross, which way is the water going to go? To the right or to the left? To the right. I'm going to have a net flow over this way because I have less water molecules. I have 3 out of 7 over here. Over here I have 5 out of 9. All right. So if this water molecule crosses over there, that process is called osmosis. Okay. So that process is referred to as osmosis. And now I have basically the same concentrations on both sides. Okay. So what's going to happen is I'm going to cross from where I'm at. Remember, the solute can't be the one that switches, only the water can go. So I'm going to go from a high solvent concentration towards a low solvent concentration to try and equal everything out. Okay? So we measure what we refer to as an osmotic pressure. And the osmotic pressure is the pressure that I need to keep osmosis from occurring. All right? So I want the two concentrations to be the same, all right? And so we calculate this as, so we use the symbol pi, which you guys have used before, okay? So we use the symbol pi for osmosis, and we say it's equal to I, so I still have a Van Hoff factor here, times mRT, okay? So now, before, remember, we were using the little m for the freezing point and the boiling point. We used molality. For osmosis, we calculate it as a molarity. It's based on a molarity. Where have we seen R before?
PV and RT.
Yeah, and PV equals nRT. So R is the gas constant, and it's 0.0821 liter atmospheres per mole Kelvin. Okay? So it's the same number that it was before. T is the temperature. All right, so let's take a look at these units for a second, okay? So I have moles per liter, that's from my molarity, all right? I have a temperature in here, so what kind of units? It's going to have to be in Kelvin because that's what's in my gas law constant. And the only units that are going to be left are going to be pressure units. What kind of units, what pressure units do you see in there? Atmospheres. So pi is this pressure and it's measured in atmospheres. Okay, so that's in atmospheres. So again, you don't need to memorize this equation, all right? So this is an equation that I would give you. So what you need to know how to plug into it. We'll practice doing that. I think there's just one slide left.
Can I ask a question before we move on?
Go ahead.
One more about this. So the particles go on the right side because the pressure on the left side is bigger because of the number of particles.
So the pressure's got to basically, yeah, the fluid pressure over here would be higher, all right?
Because of the number
Right.
of particles.
And
is
so I
bigger.
want it, right, because of, and even the water. So the water itself exerts a fluid pressure as well, okay? Yeah, so what I want when I'm using two solutions, in particular intravenous solutions, all right, is that I want the pressure on both sides of the membrane to be the same, all right? When that pressure is the same, which is going to be largely based on the molarity, all right, then those two solutions are isotonic and osmosis stops. So there's no net movement in either direction, all right? So this word isotonic means they have the same pressure, okay? They're at the same pressure, then I don't get any osmosis. All right. So there's a little blow up here, picture of some blood cells. Okay, so this is showing you essentially a picture of a blood cell, all right? And if the solute concentration outside the cell, okay, is too big, all right? So there's more solvent on the the solute, okay. So the solute out here is too high, all right? That means that the solvent is low on the outside, right? Okay? So I have low solvent, high solute. Just thought I had those drawn wrong for a second. All right? So what that means, if I have low solvent on the outside, the solvent is the only thing that can cross. And so the solvent's going to come out. So the water is the solvent. The water's going to come out of the blood cell, all right? And that causes it to basically do what we call crenulate. So it kind of shrinks up and shrivels up, okay? Exactly the opposite thing happens if I have a high solute concentration in here. That means outside I have a low solute, which is high solvent. So that means my solvent crosses inside of my blood cell, and it expands and it can eventually break, all right? And they refer to that as hemolysis, all right? This type of a solution is referred to as hypotonic, This type of a solution is referred to as hypertonic. So if you go to the hospital, so I know you guys, some of you guys work in the hospitals, okay? So when they give you intravenous fluids, do they give you water? Is that what they put in there? It's not water, is it? I hope not, because they're killing people if it is, okay? So it's not water. All right, so when you go, they typically give you either a glucose solution, all right? And the glucose solution is made up so that it is isotonic with the osmotic pressure in blood cells, okay? Sometimes they use sodium chloride. They have different concentrations that they make those up at in order to be isotonic with your blood cells, okay? So they decide what concentration to make them up at based on knowing what the osmotic pressure of blood is, okay? So that's, oh, we're gonna do sample problem. All right, so we got one sample problem here, I think. We got two, all right. So let's see if we can do a couple sample problems, and then tomorrow, so the test is Friday, right? Okay. I know. So I know we got to do it though. We got more stuff to cover. I know you guys picked this way to take this class. I didn't force you. Right? It's quick. I know. So tomorrow we're going to review. All right. I have another worksheet to do. I'll go over a couple more sample problems. So we're going to cover basically chapter 16 and through 17.10 on the test, okay? So we'll do a little practice tomorrow. It's a long period. We should be able to get some practice in, and then Friday we'll take the test, okay? All right, so let's see if we can do this problem. So it says, calculate the boiling point of a solution made by dissolving 250 grams of salt in 1,250 grams of water. So I want to calculate a boiling point. So look through your notes and tell me what equation you think you want to use. That's my equation, okay? So where did the I come from? Remember, I threw that in afterwards. I told you we're going to have to use that I.
So we're going to use them in both equations?
Every equation we use, we're going to have the I in there, all right? So I got to keep in mind the idea that if it breaks up into more than one particle, I have to account for that, okay? So let's see, where am I going to get KB? Let's see if we can figure out where we're going to find these things. What am I going to look KB up for? Water or salt? Water. I look KB up, salt's not on there. I look KB up for the solvent, okay? So I'm always looking KB up for the solvent, okay? So I look on that sheet. So this is for water. And what does it tell me it is?
0.51.
0 what?
51?
Yep, 0.51. And what kind of units does it have?
Celsius,
So I know KB, all right? It's sodium chloride, so it's salt. We're assuming it's table salt, but it's sodium chloride. I've already broken this up a bunch of times now. So what is I? Okay, I'm almost there. The only thing I don't know is the molality. All right, so how am I going to get the molality? What is molality?
moles of sodium, over the kilograms of sodium.
Moles of solute over kilograms of solvent. All right, so how much solute do I have? 250 grams, right? So I got 250 grams of NaCl. How am I going to change that to moles? So I'm going to save you the trouble. It's 58 and a half, all right, grams per mole of sodium chloride. All right, so I'm just going to figure out how many moles I have, which is 4.27. I think it's 4.277 actually. Do I have 4 sick days? Yeah, we do. We have a lot of sick days. Oh, no, we only looked at it up to 3.
No,
So let's
it
go
would be 4.
4.28.
Wait, are we rounding just 3?
Yeah, I only looked that up to 3, so I'm gonna round off. I probably should. But I only have 3 in my solid. So we got 4.28 moles.
Wait, we got 4.273.
Okay,
Just
Sorry.
4.7 would be,
okay, 4.27. All right. I probably wrote that differently in my notes. All right, how about kilograms of solvent? How am I gonna get that?
1 to 50 divided by 1,000.
So, but what number am I starting with?
1 to grams.
What's my solid? Water or salt?
water,
Water. How much of that do I have?
1,250.
Like 1,250 grams of water. All right. All I have to do is change that to kilograms. So we did this earlier, grams on the bottom, kilograms on the top. 1,000 grams per kilogram, so I have 1.250 kilograms. All right. So now how am I going to get the molality? I'm going to take these two numbers and plug in. Okay. So I have 4.27 over 1.25, and that gives me 3.42. Just a little molality. 3.42 is my molality. So now I know everything. I know I know M, I know KB, and I'm out of room. So I'm just going to plug into that equation. I can't write with that. So 2 times 3.42 M per degree Celsius. Oops, no, that's the opposite. Degrees Celsius. Oh, that's just M, right, I'm sorry. Times 0.51, this is degrees Celsius per little m. So those cancel out, all right? And that gives me a change of 3.5 degrees. So what's my boiling point? That's not my boiling point, right? That's just the change in my boiling point. So what do I have to do with this if I want to know what the actual boiling point is? Add it to the boiling point or subtract it? The boiling point goes up, so I would add it. So it's 100 plus 3.5 is 103.5. So that's a lot of work, right? All right. There's a osmotic pressure problem on the next slide. I want you to see if you can calculate this. All right. So this tells me what the osmotic pressure of blood is. It's 7.7 atmospheres. Why do you suppose we used that 36 degrees Celsius?
Have to calculate gallons, because it's a normal temperature of the body.
That's body temperature, right? Okay, so that's why we used it.
36.6.
Yeah, 36.6. Okay. So it's that's basically going to be my the body temperature. So I want to know what the concentration of glucose I would need to make up to see if I could make it isotonic with blood, because I want to know if you guys would kill me if you were calculating this. Okay. So if you had to make up a glucose solution, what concentration would you have to make it in order to give it to someone intravenously? All right. So my equation, pi equals IMRT. Okay, that's the equation I'm going to use. So glucose doesn't tell you this in this problem. This is glucose, C6H12O6. All right. What's I? What kind of compound is that?
Molecular, so it's going to be the same one.
So it's 1. So I equals 1. All right. So it's a little different in this problem is you know this, you're solving for this. You're solving for something on the other side, okay? I'm gonna let you try and set that up. List what you think you wanna put in there. This is what you think everything is, and the capital M is what you're trying to find out, all right? So see if you can figure out what to plug in there. I'm done essentially, if you wanna
Oh, okay.
take off, I'm just gonna walk around the room and look what they're doing.